What if the universe's most basic rules, the forces holding everything together, from the tiniest atom right up to the biggest galaxies, what if they aren't what we've always thought? Imagine they weren't like separate things, but maybe different sides of a single hidden reality. Today, we're doing a deep dive into something pretty radical, a new framework in fundamental physics. It suggests that the forces we know from the standard model, and even how particles get their mass, well, they don't just exist, they actually emerge. They emerge from something called coherence reductions, and it's all driven by this mathematical idea, symmetries. So our mission today is to unpack this S-Uri framework. We're going to explore how it tries to give this unified picture, connecting gauge groups, mass, maybe even dark matter. And it challenges some really big ideas like spontaneous symmetry braiding. It's definitely a trip into some complex territory, but hopefully we'll have some big aha moments.
Absolutely, and that's really the heart of it. This isn't just abstract theory. It fundamentally reframes how we see the universe's forces. They're not independent actors, They're more like facets of this single coherent structure underneath it all. And what's really exciting is it's not just neat. It actually leads to real testable predictions, things we could actually look for.
Okay, let's get into it then. Before we see how S reshapes physics, we probably need to know, what is S, just in terms of math? You might vaguely remember it maybe, but basically, S is the symmetric group on three elements. Just think of all the ways you can rearrange three distinct things. Say 3 numbered balls, 1, 2, 3. How many ways can you shuffle their order? S is the complete set of all those possibilities.
Yeah.
And it's also kind of special because it's the smallest non-abelian symmetric group, which is just a fancy way of saying the order you do the shuffling actually matters.
Right.
Swapping 1 and 2, then 2 and 3. That gives you a different result than doing it the other way around. It has exactly 6 ways to do this. 1 is doing nothing, the identity, then 3 simple swaps, like just swapping 1 and 2. And then 2 are like rotations, where 1 goes to 2, 2 goes to 3, and 3 goes back to 1.
And mathematically, this S structure, it has this really neat connection. It's isomorphic to another group, D, which sounds technical, but D describes the symmetries of an equilateral triangle. You can rotate it 120 degrees, 240 degrees, or flip it over its axis, and it looks the same. That connection kind of hints that S might be involved in structuring symmetries deep down in physics.
Okay, so in physics, S usually pops up in places like flavor symmetries, right? Like permuting quark generations or something.
Traditionally, yes. That's where you might have seen it.
But this new idea, this is where it gets really interesting.
Exactly. In this new framework, S isn't just about, cataloging permutations. It's playing a much more active role. It's described as an asymmetry resonance operator.
Yeah.
Think of it less like just sorting things and more like a filter or maybe a tuner. It's the thing that actively generates the imbalances, the asymmetries, that then lead to forces and mass emerging. It's the driver.
Okay, so let's contrast that. The standard way, in the standard model, we usually talk about forces and mass coming from spontaneous symmetry breaking, right? SSB. Like the Higgs mechanism, the universe starts symmetric, then something breaks and particles get mass.
That's the conventional picture, yes. The Higgs field plays that crucial role. But this unified coherence theory of everything, the UCTE, it flips that perspective. Instead of symmetry breaking, it talks about coherence selection effects. These effects come from those structured asymmetries we mentioned. So mass isn't just, boom, Higgs interaction. It's more like a step-by-step process, a reduction of coherence.
Ah, okay. So not a sudden break, but more like a guided selection,
Yeah.
where coherence is selectively reduced.
Precisely.
And the Higgs field itself, then, it's not seen as this fundamental particle in the same way.
In this view, no. It's reinterpreted. It's seen as a resonance operator. Almost like it parameterizes or measures the amount of coherence breaking that's happening. It quantifies the reduction.
That's a very different way to think about the Higgs.
It is. And the core idea, the central postulate of UCTE, is that the standard model forces, SU3C for strong, SU2L for weak, U1Y for hypercharged electromagnetism, they aren't fundamental separate things. Instead, they emerge. They are structured coherence reductions that come from a single higher unified structure. This unified thing is called SU321CSG, the coherence symmetry group.
Whoa, okay. So if I'm following, you're saying the forces we know, the ones we thought were distinct, they're actually just different aspects of one deeper unified force.
That's exactly the implication. They're facets of a single underlying reality.
That's profound.
And S is the key. It's the operator, that asymmetry resonance operator that breaks down the unified symmetry. But it does it in a very specific, controlled way. It's not random. And this precise S-guided breakdown is what gives us the three gauge groups we actually observe.
So, wow. This framework naturally explains why we have three forces in the standard model. It's not just a given. It comes from the math of S.
That's the claim. It falls out naturally from the structure of S.
That's definitely an aha moment.
And the mapping is quite elegant, actually. Remember those three simple swaps in S? The transpositions like 12, 13, 23?
They're just swapping two elements.
Well, they seem to map directly onto the three fundamental gauge asymmetries. So the 12 asymmetry, that corresponds to SU3C, the strong force governing gluons. The 13 asymmetry maps to SU2L, the weak force defining W and Z bosons. And the 23 asymmetry leads to U1Y, hypercharge, and electromagnetism, setting up charge quantization. It's like S provides the blueprint for how that unified force splits into the ones we see.
That is genuinely fascinating. Connecting something so simple, mathematically, like shuffling three things, to the actual structure of the forces governing reality. Amazing.
Now, let's talk mass. It's not just arbitrary values either, according to this theory. Particle masses arise because their interaction with this fundamental coherence field gets reduced, but differentially. Think of it like particles having different levels of stickiness to this field. How sticky determines the mass. The mass matrix itself is defined by what they call coherence eigenvalues, like unique energy signatures for each particle's interaction. So for quarks, you'd have eigenvalues like lambda for top, lambda c for charm, lambda u for up.
Okay, so this is a totally different explanation for why, say, a top quark is ridiculously heavy compared to an up quark or an electron. It's not just a number assigned. It's about its interaction with this coherence field.
Exactly. And the hierarchy we see, top mass, much bigger than charm, much bigger than up, that's proposed as a direct consequence of the S coherence reduction asymmetries. The S reduction process effectively swaps or tunes these coherence eigenvalues, leading directly to the mass differences we observe. And it also offers a really interesting take on dark matter.
Ah, okay. I was wondering about that.
It suggests dark matter as a coherence-bound state. So maybe not a totally new particle we need to find, but maybe it's a phase of this coherence field itself, one that's stabilized but hasn't fully decohered into a standard gauge boson we can easily detect. Its mass would still be tied to these Higgs-like coherence interactions. It's there, influencing gravity, but just not fully expressed as a normal particle.
That's a neat idea. Okay, so S seems to cover quarks, forces, maybe dark matter. But what about neutrinos? They're notoriously weird, tiny masses, they oscillate. How do they fit in?
Right, neutrinos are definitely special here too. Their incredibly small mass is seen as a sign that they are near full coherence, almost like they've barely been touched by the reduction process. This means their masses probably don't come from those initial S reductions, but from something deeper, maybe higher order coherence asymmetries. There are two main ideas floated for how they get their tiny mass. One is an extension to S permutation symmetry. S works for three families, right? Maybe neutrinos need a bigger group, S, involving four things. This could naturally bring in a hidden coherence state, or maybe a sterile neutrino, and it seems to align well with the PM and S mixing matrix that describes their oscillations.
Okay, so expanding the symmetry group, what's the other idea?
The second is called hypersymmetry reduction. It's like a cascade effect. Neutrino mass arises from a second-order coherence reduction. Their mass gets hugely suppressed by a very small secondary coherence eigenvalue. It basically forms a coherence-based seesaw mechanism. A tiny effect on one side leads to a tiny mass on the other.
That sounds like a really clever way to explain why their masses are so vanishingly small and why they oscillate. It's not random. It follows this coherence hierarchy constraint.
Exactly. And importantly, the predictions this model makes for things like neutrino mass squared differences, the mixing angles like theta 12, theta 23, theta 13, they seem to be consistent with the experimental data we already have.
Okay, moving on. Electromagnetism. Light, charge. It feels so basic. How does this coherence framework explain something so fundamental?
Yeah, U1Y, which covers electromagnetism, is treated a bit differently. It's not seen as coming directly from one of those main S swaps, like strong or weak. It's viewed more as a coherence dispersive field effect, kind of like a residual mode. What's left over when the other S asymmetries effectively cancel out, almost like a background hum. The photon field itself is described as undergoing a coherence-dependent phase shift.
Wait, so light itself isn't fixed. Its behavior is modulated by this coherence stuff. That's pretty wild. It makes electromagnetism seem much more dynamic.
It does, and this ties into another really big concept, hypergravity coherence.
Hmm.
Electromagnetism, and especially the fact that photons are massless, is interpreted as a dispersive effect of hypergravity coherence. Photons, in this view, aren't standard gauge bosons like W or Z's, they're coherence dispersive modes. And this leads to a really interesting point about how fields spread out, the difference between the usual inverse square law, 1x art, and maybe a square root law, 1x.
Ah, okay. Like how gravity and light intensity drop off with distance.
Exactly. Classical fields like E and M and gravity follow 1xr because the energy spreads out evenly in 3 dimensions. Think of ripples on a balloon. But these coherence fields, especially this hypergravity, might disperse more slowly, like 1x. The idea is maybe their influence is somehow constrained, maybe to a lower dimensional surface, kind of like a holographic idea, maybe propagating on a 2D plane embedded in our 3D space.
So, hang on. Electromagnetic waves, light, might keep their coherence over huge cosmic distances partly because they're traveling along this sort of holographic plane instead of just spreading out in 3D.
That's the implication. It's a mind-bending idea.
Wow.
And this 1x dispersion, it suggested that it naturally reduces into 1x array when you consider the full 3-dimensional radiation. It's like a precursor stage. And this could even connect back to dark matter. Maybe dark matter interacts with light by messing with this dispersion, by modifying electromagnetic field dispersion through coherence effects. You might see subtle changes in how light travels through areas dense with dark matter.
Okay, the idea that gravity and electromagnetism could be linked like this through hypergravity, that's already huge. But what about the strengths? Why is the strong force so strong, weak force weak, etc.?
Right, the coupling constants. This framework aims to unify those two. It proposes that all the standard model gauge coupling constants of the numbers telling us the strength of each force, they aren't independent values. They're actually coherence projected quantities derived from this universal hypergravity field. Imagine hypergravity as the pure source, and the forces we see are like different projections, different intensities of that source.
How does that work? How do they get different strengths?
Through what are called coherence modulation factors, symbolized by zeta. These basically represent how much of the original hypergravity coherence is preserved or expressed in each force. So SU3, the strong force, retains the most coherence. Its zeta is around 1.22. It holds on to that coherence tightly. SU2, the weak force, is intermediate, zeta around 0.65. And U1, electromagnetism, retains the least coherence, about 0.357. Which makes sense, right? It's long-range dispersive.
Yeah, that fits perfectly with intuition. Strong force is strong, tightly bound, most coherent. Electromagnetism spreads out, least coherent. That makes a lot of sense.
And this whole picture leads naturally to a coherence-based gauge unification model. At extremely high energies, the GUT scale, maybe around 10 LSV, all the forces would become indistinguishable. They'd just be different projections of this underlying hypergravity, one unified force.
Okay, this paints such a compelling, elegant picture. It ties so much together, but is it just a beautiful story, or can we actually test it? What are the predictions?
That's the crucial question, absolutely. And yes, it does make specific testable predictions. This is where the rubber meets the road. For the Higgs boson, for instance, if this is right, precision measurements should show its couplings, how it interacts with other particles, deviating slightly from standard model predictions.
Okay, so look closely at the Higgs. What else?
New gauge bosons. Colliders might find additional bosons linked to these higher coherent states, particles we haven't predicted before. Neutrino oscillations are key. Future experiments might detect subtle coherence phase shifts beyond what the standard PMNS matrix predicts. That would be big.
A clear signal. We saw that.
Also, maybe look for tiny charge quantization anomalies, very small deviations from the perfect quantization we assume, and dark matter detection changes too. Maybe anomalous neutrinos scattering in underground detectors, hinting at dark matter-neutrino coherence interactions. Or maybe direct detection experiments could see rare elastic scattering events if dark matter interacts via some coherence cross-section.
And for electromagnetism?
We might see electromagnetic deviations, how photons travel through strong gravity or dense dark matter regions. Maybe showing those coherence-modulated dispersions or slight deviations from a perfect inverse square law. Light behaving unexpectedly in extreme environments.
Wow. So there are quite a few potential avenues to check. If even just a few of these predictions turn out to be right, it would completely change physics. It's really revolutionary. So let's just recap this deep dive. The big idea is that the universe's fundamental forces, particle masses, they might not be separate things added into the model. Instead, they could be emergent structures, governed by these coherence reductions dictated by the mathematics of SE symmetries, and maybe all stemming from an underlying hypergravity. It shifts the view from like a box of separate parts to something deeply unified by coherence.
It's a profound shift in perspective, absolutely. And it leaves you wondering, if forces and mass emerge this way, what else might be a coherence selected effect? What other fundamental aspects of reality that we take for granted might actually be emergent properties of this deeper coherence? It really opens up new ways to think.
It's definitely a powerful reminder that there's always more beneath the surface, isn't there? And sometimes the biggest leaps come from looking at old puzzles with entirely new eyes. We really hope this deep dive into asymmetries and coherence has given you a good handle on what is, potentially, a truly groundbreaking idea about the fabric of our universe.